Hello, I'm going to present my report for the experiment. In this work, we estimate experimentally the value of gravity, or G. So for this, in order to obtain this value, we have to use the Marriott model of experiment 1 by emptying it with a constant flow region. It was also required to use the linear regression technique with a method of least square to obtain the values of A and B. Once we calculate these values, we figure out that the value of G is 0.03 meters per squared second plus minus 0.04 meters per squared second. As an introduction, we briefly talk about what the Marriott bottle consists, which is this device that allows the pressure to be kept constant and in which a liquid flows out of an orifice for a period of time. This only happens if the liquid stays above the bottom of the atmospheric tube. We can say that the relevance of carrying this type of experiment is for us to see how we obtain the formulas and the physical values that we know, and also to understand the nature much deeper than only acknowledging the quantity that we know. In this case, we are going to study the functioning of the Marriott bottle in order to experimentally know the value of G. For the theoretical framework, we have three key points, which is the gravity, that is defined as the force of attraction that exists between objects. This was the Newton's definition, and Einstein's definition was that gravity is a distortion of space and time rather than the force. The theoretical equation for gravity, we obtain it by taking it from the law of universal gravitation, which is the weight is equal to the mass times the acceleration. After that, we can say that the gravity can be calculated using the square root of the radius of the Earth, using the squared value of the radius of the Earth and multiplying by the result of the acceleration, which is G, and divided all by the mass of the Earth. We also see that we are using microfluid devices, and microfluid is defined as the study of the behavior of the fluids by having a precise control and manipulation of it, and these are constrained or limited to a very small scale. For the methodology, we use these equipment and materials: a Marriott bottle, the chronometer, a ruler, 3 liters of water, a computer, and a software for analyzing. The parameters that we measure, the new parameters that we are going to measure is the starting level of water, the lower level of the central tube, and the reference level, which is the drain tube, which is where the drain tube is. Then we add the diameter of the tube and the area of the tube, and also the AH, the area of the water-free surface above the level of number 2, that is calculated by this equation, which is area in minus area of the tube. We have the area H. Then we made the several tables, which are the measurements that we have our bottle, and the areas, we calculate them in the similar way as we calculate them in the experiment 1. Calculate first the area with the regular area equation, then its uncertainty with the minimum scale of the ruler, then we have the uncertainty of the radio, And after we apply all of this, we obtain that the area of the tube is this result, while the area H, we obtain it by using this formula, the area in minus the area tube, and to obtain its uncertainty, we have to sum the percentage uncertainty of each element that we are considering. So we have 2% plus 33%, it is equal to 35%. And for the area H, we have 8.9 times 10 to the minus 3 meters squared plus minus 35%. Then we made the several tables for each measurement, which was 7, 8, 9, 10, and 11 was the measurement of the H with its uncertainty, that we use the maximum uncertainty calculated in experiment 1. Then for the experiment analysis, in this diagram, we included the velocity H, with the velocity H is which the water surface lowers. So after we obtain all of this, we made with the several data of the H, the different H, we use them and put them in graphs with veils that show us the value of A and B for each value of H, which is the value of H7, the value of H8, the value of H9, 10, and 11. After that, we could measure the value of VH and VH squared. So for calculating the VH, we use the value that they'll show us, which is the value of V, and we only squared it so we can obtain the value of H squared. Well, for calculating the uncertainties, we have to make several steps. First, we calculate this part of this equation, which is Y initial minus the value of A minus the value of B in the initial. And all of this is squared. We use the values of our tables. In this case, we only are going to calculate these values of using the H equals 7 centimeters. After that, we sum the results of this small equation. And once we are done that, we have to square our values of time and sum them all. And after that, we make another sum of these times, but the result is only squared. Then we calculate sigma y, which is the square root of the sum of this small equation divided by the number of elements that we have in our table, -2. Then for delta, we use this. We have to multiply the number of elements of our table times the sum of the squared times minus the sum of the result of the times squared. Finally, we can calculate the uncertainty of A and B. For the uncertainty of A, we use this formula or equation that is sigma y times the square root of the sum of the square times, this divided by delta. And this is the percentage, and we want to obtain the percentage, so we use this formula that is the uncertainty times 100 and divided by the value of A. Then for B, we made something similar, but we changed the sum of the times squared for the number of elements. And for the percentage, we do the same as A, but with the values of B. And in this case, because of the limitation that we have, we only take the percentage uncertainty of only one measure, and in this case is 3%. After we obtain all of our BH squared, we can make our graphs, and it is the BH squared for different values of H. Then we estimate the values of C and G. For the estimation of C, we use the value of B that shows values, and we put it here. And for G, we use this equation, which is 1/2 times the area H divided by the area out, all of this squared times C, which times C is the value of B. Then we substitute our values and we obtain that the value of G in this case is 294 meters per square second. In order to find its uncertainty, we have to multiply 2 times the percentage uncertainty of area H plus the percentage uncertainty of area out, and we sum the percentage uncertainty of C. Then we substitute our values that we previously calculated before, and we have that the percentage uncertainty of G is 142%. Then we find out what's the exact value of the uncertainty, and we conclude that the value of G is 0.0 per meter squared plus minus 0.04 meters per second squared. Well, for the discussion, we can see that the graphs of H and the time, they are pretty similar for the, or it looks like the expected ones, despite some points that go very far off the fixed graph. And on the other hand, we have the graph of the value of H squared for different values of H, that it doesn't appear as the expected graphs. And also because it is more dispersed, it looks like it is without any slope. Nevertheless, if we analyze it deeply, we can see that somehow the line continues as the expected one, but it isn't as evident as the expected one. So for this, we can say that the value of G is 0.03 meters per squared seconds plus minus 0.4 meters per squared seconds. And in this experiment, we see that the graphs are very dispersed and the results are very different because of the errors present. And in this case, we have two types of errors that were measurement errors. That one was the random error because of the way we were taking the heights. The angle that we see the bottle and we take the height was very important because from one point of view, we can see one measurement, but from another point of view, we see another total different measurement. So that was one of our errors, our random errors. And also because we were analyzing them by videos, it was difficult to know the exact number. Regarding to the systematic errors that are the ones that they are produced because of problems of measurements, or if we introduce something that has a possibility to alternate the results, that's the systematic errors. And this kind of errors are very difficult to notice because we may sometimes not know the instrument very well, so we don't know when the instrument is going to fail or it has some problems and does not make the measurement right. But also in other occasions, we trust ourselves and we do not calibrate our instrument, or we don't change them to something more precise. Some of our errors in this case, we have the the timer of our phone. Our phone was failing, so the timer was a little bit slow. So that was one of our errors. And another error was the scale that we use, because we use a written scale on the bottle, and we didn't use the correct measurement instrument as a ruler or something more precise. So that could affect the precision of our results. For the conclusion, we can say that in this work, in this work, we estimate the experimentally value of G. We use the Marriott bottle experiment, and we took different values of H and made its graph in order to make the fit fix or to use the linear regression using the least squares method. And we can obtain the values of A and B, so we calculate the VH and the value of G. We find out that in this case, the value of G is 0.03 meters per squared seconds, plus minus 0.04 meters per squared seconds. And the percentage uncertainty of this corresponds to 142%. Then it can also be seen that the discrepancy between the experimental value and the theoretical one is approximately 9.78 of this. And because it is a big difference, it can be considered a really big, a significant discrepancy. And also, taking the these two values, it can be said that the theoretical one does not lie within the uncertainty range that we obtained of our experimental, because the maximum of our experimental is 0.007 and the minimum is minus 0.01. So the theoretical value is out of the range. To sum this up, it is possible to say that the experimental result obtained does not match the theoretical one, and therefore it isn't a precise value because it has a really high discrepancy, and it doesn't lie on the range also, so it could not be a reliable value, and it is not accurate to use. One limitation that we notice is the part of the measurement instrument, as we said in the previous discussion section. We mentioned that the scale was very limited and it was not precise at all. And to conclude all of this, it is important to mention that making this type of experiment show us what's behind the nature of things and how they work with the point of view of the physics. It also helps us to know a better understanding. So with this can help us in the future to solve diverse problems of our daily life and professional lives.